Section. Introduction. We're focusing on improving the ability of deep learning models to handle long-range data, which is crucial for analyzing time series data and processing long-form data like text, speech, or videos. This challenge has two parts: effectiveness and efficiency. While many researchers have proposed transformer variants to address the efficiency issue, we're concentrating on the effectiveness problem. This is because transformers often struggle to use long context effectively, and this issue has been highlighted by the Long-Range Arena (LRA) benchmark. Our research is inspired by recent advances in deep long sequence modeling. We're trying to understand why certain long-range layers perform well on the LRA benchmark and other long-range tasks. We've identified two key conditions for success: an exponential decaying positional structure and a regularized smooth global operator. Based on these principles, we've developed a new variant of attention called local and smooth attention, loss attention. Our tests show that this layer can improve transformer performance on long-range tasks, with only a small increase in complexity compared to standard transformers. Our main contributions are as follows. 1. We provide theoretical and empirical insights into long-range sequence modeling and identify the properties needed for success in long-range tasks. 2. We show that a smoothness promoting inductive bias and positional locality are crucial for capturing long-range dependencies. 3. We introduce a new variant of attention that is effective in capturing long-range dependencies. 4. We present a version of loss attention that meets both effectiveness and efficiency criteria, by having a linear complexity while maintaining high accuracy compared to other transformer variants. 5. We provide the first layer that doesn't rely on 1D long convolution and yet achieves an average score higher than 70 on the LRA benchmark. We acknowledge that our results may seem counterintuitive at first, as locality and long range are often seen as opposing concepts. However, this is explained by the fact that long-range layers capture faraway dependencies through a hierarchical combination of local dependencies. We also discuss the background of global convolution layers and long-range transformers. Global convolution layers are a fundamental building block of deep learning. They have three main advantages. They can operate over an unrestricted context, they have a sub-quadratic time dependency on sequence length, and they are regularized by design. Transformers have emerged as highly effective models for various tasks. However, their widespread adoption has been challenged by the quadratic cost of the self-attention mechanism and their poor performance on long-range tasks. Many approaches have been applied to overcome this challenge and to create efficient transformer architectures. Finally, we discuss alibi, a method that enhances length extrapolation in transformers by adding a positional-based linear bias to the attention scores. It computes attention by considering the distance matrix of the sequence length multiplied by the causal mask. Section Summary. Enhancing the long-range capabilities of deep learning models, particularly transformers, is crucial for real-world time series analysis. While researchers have proposed transformer variants with sub-quadratic complexity to address efficiency, our work focuses on the effectiveness aspect, which is a critical bottleneck. We introduce local and smooth attention, loss attention, a variant of attention that adheres to the principles of exponential decaying positional structure and a regularized smooth global operator, which significantly improves transformer performance on long-range tasks. Section. The Long-Range Arena (LRA) benchmark. In recent times, we've seen a surge in the development of long-range transformer models. These models are designed to tackle the challenges of scalability and performance that come with handling long sequences in transformers. The Long-Range Arena (LRA) benchmark has become a popular tool for evaluating these models across a range of scenarios, tasks, and data types that involve long context. The LRA benchmark tests models on sequences ranging from 1,000 to 16,000 tokens, covering text, visual data, and mathematical expressions. Recent findings show that global convolution layers, such as S4, outperform transformers on this benchmark. Our research begins with a thorough investigation into why transformers don't perform as well as state space layers and long convolution layers in long-range modeling. We focus on the transformer's ability to model long-range dependencies, looking at expressiveness, optimization, and generalization. Our goal is to identify the main bottleneck. We argue that the subpar performance of transformers on long-range tasks isn't necessarily due to issues with optimization or expressiveness, which are inherent to the architecture. Instead, it's likely a matter of generalization, which can be effectively addressed by incorporating the right inductive bias. This insight led us to explore the nature of long-range inductive bias and how it can be integrated into transformers. Transformers are high-capacity models, so it's unlikely that expressivity is the main issue in long-range tasks. We make 2 points to support this. First, we found that large transformers can achieve near 100% accuracy on the LRA benchmarks, including the validation set, showing their ability to handle these benchmarks. Second, we demonstrate that a single layer of a transformer, with a sufficient number of heads and a large hidden dimension, can express any state-space layer with the same number of channels. This is because each channel of the state-space layer includes a long convolution kernel, which can be expressed through the attention matrices. Our proof applies to any kernel, not just those constructed through state-space parametrization, further clarifying the relationship between transformers and global convolution layers. Long-range dependencies often come with optimization issues, such as exploding and vanishing gradient problems. However, we argue that this isn't the main bottleneck in transformers for 2 reasons. First, unlike RNNs, transformers process tokens in parallel using the self-attention mechanism, ensuring direct interaction between all pairs. This means there's no reason to believe that gradients are more likely to vanish or explode on long interactions than on short ones. Second, transformers use normalization layers and residual connections, making them relatively stable. We propose that the main reason for the suboptimal performance of transformers on long-range tasks is likely a lack of generalization, caused by an unsuitable inductive bias. In other words, existing transformers tend to overfit the long-range data. We support this claim with 2 observations. First, models that perform exceptionally well on LRA benchmarks often contain layers with strong inductive bias. Second, our models show significant improvement on the LRA benchmark as the amount of data increases, which isn't the case for other transformers. This suggests that with the right inductive bias, the model's ability to fit the underlying data distribution improves. We start by exploring ways to incorporate suitable inductive bias into the transformer architecture. We observe that long-range layers often promote exponentially decaying kernels and kernel smoothness. We then explain how we incorporate these principles into the attention layers. We believe that incorporating inductive bias can help to bridge the generalization gap. However, the existence and specific characteristics of such inductive bias remain unclear. To address these questions, we aim to identify the common principles underlying the design choices in layers that successfully capture long-range dependencies. Given the wide variety of long-range layers, including state-space layers, toplets NNs, linear diagonal RNNs, and long convolution layers, and the fact that these layers are built on many design principles, discerning the exact reasons why these layers perform well, especially when compared to transformers, is a challenging task. We, therefore, delve into the investigation of those layers. A common design choice in long-range layers is to use convolution kernels with an exponential decaying structure. This trend of exponential decay can be seen in the kernels through initialization, parameterization, or computation. All these convolutional kernels have a decaying structure, meaning the weights for interactions with closer neighbors are larger than for those with more distant ones. It's also suggested that having regularized convolutional kernels is essential for capturing long-range dependencies. Following this, it's empirically demonstrated that smoothness can be a powerful tool for kernel regularization. This smoothness can be achieved by reducing the size of kernel weights in the time domain using a squashing operator, which enforces sparsity, leading to smoothness in the frequency domain. Moreover, layers such as EMMA or linear state space layers are naturally smooth in their design. Section Summary. The Long-Range Arena, LRA, benchmark is a dataset used to evaluate the performance of long-range transformer models. While transformers have been shown to underperform on long-range tasks compared to state space layers and long convolution layers, it is not due to issues of expressiveness or optimization. Instead, the primary factor is likely the lack of generalization caused by an unsuitable inductive bias. By incorporating appropriate inductive bias, such as exponentially decaying kernels and kernel smoothness, into the transformer architecture, the performance on long-range tasks can be improved. Section. Local and smooth, loss, attention. We're going to delve into a concept we call local and smooth, loss, attention. This is a mechanism that tweaks the attention computation by adjusting the attention matrix to include a long-range inductive bias into the attention operator. We're not sure if these principles are relevant only to convolution kernels or to any global operator, so we're exploring this empirically. To give you a visual, we've provided a detailed depiction of the loss attention in a figure. We've implemented the principle of smoothness by applying 1D average pooling to each row in the attention matrix. The principle of exponential decay is enacted by multiplying each element of the attention matrix at each head with a non-learnable locally decaying matrix. Just like self-attention, our local and smooth operators can handle unrestricted context with varying lengths. In formal terms, one head of self-attention is given as a certain mathematical formulation. Based on this, we can define the loss attention head. Here, AP denotes an operator that carries out 1D average pooling individually for each row of the attention matrix. If we have an input sequence of length L, the dimensions of the attention scores and the exponential decay are both L by L. We apply average pooling with corresponding padding to keep the same shape as the original attention scores. Our loss attention has two operators, the smooth operator implemented by AP, and the local operator implemented by the exponentially locally decay, ELD, operator. The ELD operator is defined by a certain mathematical formulation, and we define the ELD matrix in a similar way. To keep the exponential decay trend, we need to establish directionality within the model. That's why we consistently use causal models in our work. We achieve this by defining the matrix DL as the distance matrix multiplied by the causality mask. Our added mechanism doesn't add much computational overhead and doesn't introduce any additional learnable parameters. To control the decay rate in the CTH attention head, we use different values of alpha_c across various attention heads. We use distinct alpha_c values across the attention heads, instead of per position in the sequence. This allows each head to focus on dependencies of a uniform scale, and provides a natural way to operate on sequences with varying lengths. This way, the model can capture a range of local dependencies at multiple scales within each layer. This helps the model recognize global dependencies at the level of the entire model, creating a mix of local interactions that translate to global long-range dependencies. We've provided sample LDM matrices for different values of alpha_c in a figure. The ELD matrices are Toeplitz matrices, which can be represented by their first row. The first row values for different values of alpha_c are shown in the same figure. These Toeplitz matrices look similar to convolutional kernels, especially with simpler global convolution layers, like MEGA. To encourage attention heads to focus on different types of dependencies, we regulate the effective lengths of the LDM matrices across distinct channels. We do this by creating a sequence of evenly spaced alpha_c values in exponential space. To make it easier to compare with standard transformers, we set alpha_o equals 0 in the first attention head, and remove any positional decaying bias, which results in a standard attention head. We initialized alpha_c in a certain range, where b is a hyperparameter in the interval 0, 1. We've tested our method on standard long-range benchmarks. We first compare loss attention with other transformer variants and long-range layers. Then, we justify our design choices by testing each of the model's components. Finally, we investigate how various factors, like the amount of training data and the context length of the attention, influence performance. We've kept the experimental setup consistent across all subsections, and we've described it in detail in the appendix. We've also included additional experiments in the appendix. For example, we've visualized the attention matrices of loss attention, and we've detailed the evaluation of loss attention on NLP tasks. Section Summary. The local and smooth, loss, attention mechanism incorporates a long-range inductive bias into the attention operator by adjusting the attention matrix. It implements smoothness through 1D average pooling and exponentially decaying principles through element-wise multiplication with a non-learnable locally decaying matrix. This mechanism allows for the recognition of global long-range dependencies while maintaining computational efficiency and without introducing additional learnable parameters. Section. Results on long-range tasks. In this section, we'll discuss our findings on tasks that require long-range processing. We'll focus on the long-range arena, LRA, benchmark and variations of sequential MNIST. We compared our method with several previously published models that use transformer-based models and long-range layers. Our method, which we call loss attention, consistently outperforms other transformer-based methods, including strong competitors like reformer, linformer, and performer. It even surpasses the previous best model, Luna Transformer, by a margin of 12.04%. In the image task, our model outperforms all other transformer variants by at least 22%. We believe this is due to our method's inherent bias towards smoothness and locality, which is beneficial not only for long-range tasks but also for natural signals like vectorized images. We also propose a variant of our method, called loss chunk attention, that breaks input sequences into fixed local blocks of size 128. This ensures minimal loss of local information. This variant outperforms all transformer methods on all tasks, except for the Pathfinder task. It even outperforms more computationally intensive models like vanilla transformers, which compute the full attention matrix and have a quadratic complexity, with an average accuracy boost of 11.34%. However, compared to long-range layers that incorporate global convolutions, like Mega and S4, our method doesn't perform as well. This suggests that we can learn more from these layers to improve transformer architectures and understand the shape of long-range inductive bias. One possible reason for this performance gap could be the difference in directional processing. Our models operate in a causal, unidirectional manner, while the global convolution layers in the discussed methods, except for S4v1, use bidirectionality. In fact, moving from unidirectional processing in S4v1 to bidirectional processing in S4v2 was a key upgrade. This suggests that adopting bidirectional processing in loss attention could further decrease the performance gap between transformers and state-of-the-art long-range layers. The sequential MNIST tasks present a challenging problem by treating 2D images as vectors. This setup ensures that the spatial relations present in the original images are reflected as long-range dependencies in the vectorized image. A variant of this task, permuted MNIST, scrambles the order of pixels in each image, making the task even more challenging. Our loss attention improves performance on both tasks. For instance, on sequential MNIST, the local and smooth operators boost performance by 0.28%, improving the scores from 98.90% to 99.18%. On permuted MNIST, performance is boosted by 0.15%, from 97.90% to 98.05%. We also conducted additional experiments on the LRA benchmark to understand the contributions of each component of our model. We found that each operator contributes to the success of the method. For instance, removing the smoothness operator, loss attention significantly outperforms L attention. Similarly, when the contribution of the ELD operator is removed, loss attention surpasses the resulting S attention. Our exponentially locally decaying ELD operator and alibi manipulate the attention matrix via the distant matrix, but with different motivations and impacts. Alibi was created to achieve length extrapolation, whereas our operator is designed to integrate a long-range specific inductive bias into the attention mechanism. In terms of performance and long-range capabilities, there is a considerable margin between the methods. The additional exponential decaying structure significantly contributes to enhancing the long-range capabilities of the model, as reflected by an average improvement in accuracy when not using the smooth operator, and when smoothing is added to both. Section Summary. In this section, the authors present their findings on long-range tasks, comparing their loss attention model to other transformer-based models. They show that loss attention consistently improves performance on all evaluated tasks, outperforming previous models by a significant margin. They also propose a variant called loss chunk attention, which segments input sequences into fixed local blocks and achieves better performance than other transformer methods. However, compared to long-range layers with global convolutions, their method exhibits suboptimal performance, suggesting that there is more to learn from these layers in improving transformer architectures. Additionally, the authors discuss the performance of their model on sequential MNIST tasks, where loss attention enhances performance on both tasks. They also analyze the contributions of each component of their model and compare it to the alibi method, highlighting the differences in motivation and performance. Section. The impact of data quantity and context length on long-range tasks. We're exploring how the amount of data and the length of context affect tasks that require long-range understanding. We're particularly interested in seeing if our loss transformer can handle these long-range dependencies. To test this, we tweak the context length in the attention layers by gradually reducing the size of the chunks. This forced the model to learn interactions up to the maximum length of each chunk. We then tested these models on a subset of the LRA benchmarks, which included tasks related to images, text, listops, and Pathfinder. Our findings, as shown in the figure, revealed that as the context window became narrower, the performance significantly dropped. This suggests that our loss attention model can greatly benefit from a wider context. We also wanted to understand how the size of the dataset impacts the performance of our models on long-range tasks. So, we ran experiments with different amounts of training data and observed their effect on the model's accuracy. The figure shows that as we increased the amount of training data, the performance on all tasks, including images, text, listops, and Pathfinder, consistently improved. This indicates that the more training data we have, the better the transformers perform, potentially closing the performance gap with long-range layers. This trend supports the argument we made earlier, suggesting that the main challenge for transformers on long-range tasks is the generalization gap, not optimization or limited expressiveness issues. We believe this gap can be reduced by a more suitable inductive bias. In our discussion, we argue that developing theories, tools, and well-defined concepts can significantly improve the long-range capabilities of modern AI systems. A clear example of the need for such tools is shown in a study that empirically demonstrates that language model learning, LLMs, even when trained on extensive data, struggle to use long contexts. In some cases, performance continues to decrease as context length increases, especially when crucial information is located in the middle of the context. While layers like mega and state space layers achieve excellent results on long-range tasks, it's still unclear if these layers can scale as well as transformers, and how they should be scaled up. Therefore, finding alternative mechanisms and identifying the bottlenecks that prevent transformer success in long-range tasks is an important area of research.